And now if we want dl by dyl is nothing but for all the out and outs one dimensions for all the classes dl by dzl gzl by dwjl. So that is nothing but this thing previously what we have got, and dzl by dwjl is nothing but xj input, because the equation is something like simple equations like here. So with this, with respect to dz with respect to dw's, we get xj's only. As the equation is something like that, dzl with respect to dwjl is nothing but xj, right? So that only we are getting over here. We got the equation derivative of dzl with respect to dwjl, we will get xj only. That was the equation derivative of dzl with respect to dwjl, dzl j is equal to 1 and out with respect to derivative of dzl with respect to dwjl, it will be xj only, right? Because this with respect to this we are doing, so this will be the constant over there, and this will be the variable with respect to which we are doing. Derivative of dzl with respect to dwjl will be xj. So that only we are putting it over here. So that's nothing but loss in weight of fully connected layer. So whatever the things which we have got, the loss with respect to w's, we will be using those things for this weight. So all these are weights, so we will use those derivative of loss with respect to weights to train our neural network till here. So all those weights will be updated using gradient descent, which we have talked previously. This one. So now whatever the things which we have, we need to use those derivatives to backpropagate that, use that also in pooling layer and convolution layer. I have shown that in the previous parts, previous part of the video. I have just shown you in the previous parts. I have shown you how we will do backpropagation for convolution pooling. Like for convolution pooling also similar, but again in some intuitive terms I can just show you. For example, this is an input image, and if you apply max pooling is nothing but we will take that filter like this. This is a slide we will take. Filter is nothing but just like window we will take. Now here we don't have any physical filters like we do in convolution operation, like logical filters we don't have. So here what is the maximum term? 8. So we'll just go for that, and for stride 1 we are taking for this example, we will go over here and it is 9. For stride 2 this is 9, and this thing 8, 9 for stride 2. For stride 1 the size will be different, dimension will be different. So then whatever the backpropagation, whatever the derivative of weights we will get to pooling layer, with that we will form dl by dx. dl by dx is nothing but matrix of gradients for those biases terms. So now this 8 is present in this place of the input, so this gradient is used to backpropagate and form a matrix of same dimension. Here also same dimension of the bias and input same dimension, but these derivatives, as you can see, different shade. This thing is propagated over here, and this thing is propagated over here, and this thing, and I'm just shading different colors. As you can see, I will just show you in numbers 1, 2, 3 different shades I gave, different angles, but I'll just give number 1, 2, 3, 4. So it will be 1, 2, 3, 4. So in that place this gradient will be placed, and for all others it will be 0. So this is nothing but backpropagation or derivative of loss with respect to convolution layer. Derivative loss with respect to bias is this, which we are calling x. So this we are calling x dash. This is backpropagated to change the filters. dl by dw, we are going to change that using this x dash. So basically using dl by dx dash and convolution layer, in convolution we have weights, so for that derivative loss with respect to weights we will find, and then again gradient descent we will apply as discussed previously, this thing. And again this is intuitive example, but we have showed you previously, like in mathematical and from scratch, in mathematical terms we have shown in previous parts. So this is the intuitive idea of how from fully connected layer we will backpropagate through pooling layer and then to convolution layer. And again convolution and pooling layer, convolution is discussed mathematically in previous parts, and that same goes to pooling also a bit. Now we have just shown you for fully connected and dense layer in mathematical terms, and how we can just backpropagate that information through pooling and convolution using this dense layer derivatives in an intuitive example we have shown again. So full mathematical parts of all those layers and intuitive example have been discussed now of convolution, pooling, and fully connected and dense layer. Now for just an example of forward propagation of CNN, we are just using cross correlation or convolution operation on this input image using this filter or kernel. So we'll just this thing, if you just use valid only, just an example, all will be zeros. All are zeros means we will get 0 only, and again for all the zeros we will get 0 only. If we take this as different also, like 2 is over here, 4 is over here, 0 0 0 0, and if we'll do operation also again 0 only. So dl by dw, so whatever the weights are there, we are getting input only. That means whatever the filter we are using, we are getting filter again. So that is nothing but out of ij is convolution operation of image and filter. So these are weights, right? So whatever the weights we are taking, the same input we are getting. Same input means whatever the input of the weights we are getting, that only that thing only. So it's nothing but 3 by 3. For example, this is 3 by 3 filter. We'll just run through it, right? And again, this is a filter. We are not using subdomain. We have to take totally. So we will just apply totally, right? We will apply totally.